Apparently, yes. So now you're on. So now you can say hello to anyone. Okay. All right, guys. Good morning, everyone. Did you have a good weekend? It was a great weekend to go outside, right? Spend time outside. Go to Barton Springs, to the river, or to the creek, anywhere. Do a barbecue. All right, okay, guys. So I'd like to start talking about the homework. So we talk about the homework solution, and then we continue with wellbore stability. All right. So your homework should be graded by now. Yes.
When are you going to upload the next chapter?
The next.
The chapter on wellbore.
Oh, so I'm working on that right now. You see, these are my notes and what I have to change, what I have to add. So I already put all of these, and I wrote everything, but I have to just look for mistakes and do some minor changes or some big changes sometimes, and then I'll add it. Hopefully this will be ready by Thursday. Okay? Yes?
Also, you saw Lab 4 assignment on Canvas. I don't know if you're going to take that down since we did it in the homework.
Oh, okay. I'll change that. Yeah, I can do that.
So we should officially have no Lab 4 due, right?
No. Your lab 4 would be the wellbore stability lab. Okay. All right. So let's talk briefly about the homework. Let's see the first problem. The first problem is a case in which we are taking advantage of this property of faults that they limit the stresses in the subsurface. So the main concept here is that tectonic stresses can add stresses or can lower stresses in sedimentary basins, but there is a limit for that. And that limit is the shear limit. So remember, if we have here, this is sigma and this is strain, in some regions you may expect to have a linear relationship between stress and strain, but at some point you're going to go into a flat region. That's the region in which the faults occur and the faults start to control the stresses. You cannot go forever high in stresses in the subsurface, especially if we are more rigorous on stress anisotropy. So let's see how to solve this problem. Basically, this is the solution. You have to assume a stress, and with that stress and a friction coefficient, then okay, it's still working good. With those stresses and a friction coefficient, you can tell what can be the absolute lowest value of the minimum principal stress if, for example, you were in normal faulting, or the absolute maximum if you were in reverse faulting. So in this case, as we always do, the first thing that you have to do always is to calculate the vertical stress. The vertical stress is relatively easy to calculate. It's just the gradient of vertical stress that, for example, if you were doing a real problem, you will do it from the well logging data. And as soon as you calculate that, and if you know that this is normal faulting, then you calculate what is this effective maximum stress, which is sigma 1, and the absolute minimum value of sigma 3 is going to be always sigma 1 divided by Q, right? And Q, in this case, if you have a friction coefficient of 0.6, is 3.1. So if we know that this is sigma 1, sigma 3 is going to be about a third of that. And this is going to be sigma 3. You add that to pore pressure, and you get your minimum principal stress. So what this is telling you here is that minimum principal stress is more than pore pressure, and it's in between pore pressure and the minimum principal stress. But the relationship between those two is just linked by this relationship, which is unique, either if you are in normal faulting or in reverse faulting. In reverse faulting now, you have a different case. You know, it's still the SV is the same, but now you know that you're in reverse faulting, and you know that the absolute maximum value is going to be, if this is reverse faulting, now this is S3, the minimum principal stress, and therefore this is going to be sigma 3. So sigma 1 for this case is going to be about 3 times sigma 3. So that one is S1, and since this is reverse faulting, this is going to be SH max. So all of these problems, they just consist on recognizing what is sigma 1 and what is sigma 3. And that depends on the faulting regime. The continuation of this problem is to use a different friction coefficient equal to 1, and that gives you a bigger number for Q. And that Q is also called sometimes a stress anisotropy factor or stress anisotropy ratio, because it tells you what can be the maximum stress as a function of the minimum stress. So if you have a bigger friction coefficient, if your fault is stronger, then you can sustain a bigger difference between sigma 1 and sigma 3. So let me zoom out over here. If you see these ones where this is about a third of that one, if you have a bigger friction coefficient, now this one is going to be more or less a sixth of that one. So if you had a stronger faults and stronger rocks, your minimum principal stress could be lower than the case before with a smaller friction coefficient. And the same with reverse faulting. If you have stronger faults, they could go higher into the value of SH max. And again, if I were to make the comparison with sigma and strain, we're saying that, for example, this one will be mu equal to 0.6, but something stronger will go to a higher level, say mu equal to 0.1. No, it's not 0.1, it's 1. So let me ask you the following. So are we okay with this one? So remember, that value Q, it tells you the strength of the faults and tells you what is the maximum difference that can be between these two maximums, the maximum and the minimum stress. If we were in strike slip, how would you calculate the maximum stress, the maximum horizontal stress? According to this theory, without tectonic stress, what would be the maximum possible horizontal stress? So notice that in these two cases, we sort of anchored to SV. We know SV, we know pore pressure, and we can calculate either in normal faulting, we can calculate S3 or SH mean, or in reverse faulting, we can calculate SH max. What is the maximum principal stress in strike slip? SH max. And the minimum principal stress? SH mean. So in strike slip, actually, the vertical stress is not going to help you. It's not going to help you determine that. But alternatively, what you can do, so if we were to have strike slip, you cannot use SV. Still is the same relationship. But now, this is going to be SH max minus pore pressure, right? This is going to be the same Q, and this one is going to be SH mean minus pore pressure. So let's assume that we know Q and we know pore pressure. The only unknown here in order to determine SH max, which is usually a value difficult to determine, will be to measure this one. How do you measure that one? Step rate test, usually step rate test is for continued injection. Better than that, you will use either the leak-off test or any hydraulic fracture test. That's going to tell you what is the minimum principal stress. And as soon as you have that value of SH mean from any of those tests, you could tell what is the maximum principal stress in strike slip. But notice that in that case, you cannot use SV. You need additional information. Okay. I'll continue problem number 2. Problem number 2 is a very similar problem, but now it goes into an application example in which you have to do a few more numbers. So exactly as we have done before, if you can calculate, if you want to calculate stresses in the subsurface, now using this other theory, first of all, you will have to calculate what is your maximum principal stress, vertical stress. Second, you will have to calculate what is your pore pressure. In this case, we know that there is overpressure. And after that, you get effective vertical stress. And as soon as you have effective vertical stress, knowing that this is under normal faulting, everything you have to do is just apply this equation, which is going to be the same all the time. Remember, these are effective stresses. These are not total stress, okay? That's going to give you a value that is not correct if you use that one. And after you get effective horizontal stress, then you just add pore pressure and you get what is the value of the total horizontal stress. There is something very important to notice here conceptually. Look, try to concentrate on this plot. So if you had hydrostatic pore pressure, this is what you would see, right? And your sigma 1 would be from here to there, and your sigma 3 would be, in this case, about a third of that, because Q is equal to 3, right? If it's a third, it will be somewhere over here. But notice that as you increase pore pressure and as you have overpressure, that sigma 1 gets smaller and smaller. You see before, if you had hydrostatic pressure is here, if you had overpressure is from here to here. And a third of this thing is smaller than the third of what I had before. And the consequence of that is that as you have more overpressure, the state of stress tends to be more isotropic. The stresses are more similar to each other. So if this is going to be SV in this case, this is going to be SH mean. It's actually pretty similar or pretty close to that value. And the closer you go with pore pressure to SV, the more isotropic the state of stress is going to be, and the smaller the effective stresses are going to be too. If you have small effective stresses, by now we know that your rock is going to be weaker. More stress, more effective stress makes the rock stronger. Lower effective stress makes the rock weaker. And therefore, if you go to some of these places and you drill with significant overpressure, usually if you have lots of overpressure, your rock is weak and your wellbore stability is not great. And that's something we're going to see as we move into wellbore stability as well. Okay, so if you plot the Mohr circle of that, effective stress more circle always sigma v is 378, that point over here. Sigma h mean is that value 126, that is the Moore circle with overpressure. Without overpressure, if I assume no overpressure, this will be the Moore circle. And notice that in this case, with overpressure, the Moore circle is much stronger than without overpressure. Without overpressure, you can have larger effective stresses. And with overpressure, the Moore circle gets smaller and smaller. I don't know if there was something else here to do. Draw the Moore circle, and no, that's it. Any question about this problem? No? Okay, I'll move on then. I think here is where you may struggle a little bit more. The other ones are relatively easy. So in this case, what you have to do is to find the orientations of ideal open mode hydraulic fractures and shear fractures created under a, in this case, it's a reverse state of stress, reverse faulting, and you know that SH max is going in that direction. So the first thing I would do in this case is to kind of draw a cube or a top view with the stresses in there, without drawing any faults, any fractures, any nothing, just to have an idea about what you're looking at. Okay? So in this case, SV, SH max, east-west direction, SH mean. Okay? The second thing, the easiest thing to do now is to look for the hydraulic fracture ideal orientation. Hydraulic fracture is going to be always a plane perpendicular to the minimum principal stress, which in this case is S3. So this is your hydraulic fracture. What is the strike and dip of that? Well, strike, it doesn't have a strike because it's a horizontal plane. And as long as you put there a horizontal plane, that's fine with me. And what is the dip? Is 0 because it's a horizontal plane. Okay? Are we all good with that? Okay, second step. Second step is about the shear fractures. The shear fractures, before you do anything here, always remember that the ideal shear fractures are going to happen as you did in lab several times. Triaxial, uniaxial. Always you load it in this direction and the rock breaks like this, right? And if you remember that, that's almost 70% of the solution. The only thing that you have to do here is just to orient this one into your problem. Just put it, in the orientation of the problem, and that's it. There is one more thing here to consider, which is where is the minimum principal stress. You need two stresses here in order to define these two planes. So in this case, you see this is the same thing. S1 in this case is SH max because it's reverse. So it goes in this direction. And the other piece of information that we need is S3. And S3 we know because it is reverse faulting, is in this direction. So the rock is going to break in such a way that you're going to have faults oriented steep relative to this plane. And those are going to move always in the direction of S3. Why they move in the direction of S3? Because that's the lowest minimum principal stress. They wouldn't move in direction of S2 because that wouldn't make sense, right? Why you're pushing like this and there is more stress on this side and this side? Why would it move like like that. It's not going to break like this, because it's not going to move in this direction, because this one is higher than that one. It's going to move always in the direction of the lowest one. So if this piece of rock were to move, it's going to move in this direction and in that direction. So it's going to slide like this. And it's going to be exactly the same if you have this one coming from the other side. This one is going to slide like that. The next step here is to recognize the angle. But first, remember always that this is going to be a steep angle from the plane of the maximum principal stress. That angle that is going to be always between the plane of S1 going to S3. Imagine that you have a hinge in here. So this is always a hinge. It goes from here, that will be an angle equal to 0, towards the plane of S3. That angle alpha, or beta, we call the beta 2 in some of our notes. It's going to be always this, 45 degrees plus friction angle divided by 2. But remember that that angle is not necessarily the dip. That angle can be the complementary angle of dip, as in this case. Like the dip is not that angle, the dip is going to be 90 degrees minus that. So it's going to be that angle over here. And in cases of strike slip, it's going to be related to the strike of the fault, not to the dip. So the dip of these faults is going to be 90 degrees minus that, which is this angle. And in this case, the strike is going to be north-south. Both of them strike north-south. One of them strikes towards the east, dips towards the east. The other one dips towards the west. And this is the solution for the shear fractures. Any question about this problem? I encourage you that, I forgot my cards again, but if you want to have some visual aid about this problem, you can have a piece of paper. I'll allow you to have that in the exam too, that looks like two planes here, like a cross. And as long as you remember that this is S1, and then you have to orient this according to your particular state of stress, that's fine with me. Okay? All right, and if you want to stop by my office and talk a little bit with me, I'm very lonely over there, so if you stop by, just say hi. I'll give you a free sample, okay? All right, it's very useful, okay? Those two planes are very useful in order to realize how this will orient. Normal faulting is relatively easy, but reverse faulting, strike slip, it gets more complicated. Okay, so any question about this problem? Number 3, we're good? All right, let's go to number 4. Number 4, so this is reverse faulting. Now, number 4 is with strike slip, okay? And this one is a little bit more complicated. In strike slip, always the hydraulic fractures and the faults are going to have a dip of 90 degrees. Those are going to be vertical planes. And because of that, it's just going to be easier in this case to draw just a top projection of that. So in this case, we know the first thing to do is always to draw and to recognize, identify what is the direction of the principal stresses. In this case, SH max is going this direction, 20 degrees from the west towards the north. So this is also 20 degrees. And perpendicular to that, we know we're going to have SH mean. And the first thing that you have to do here is to try to recognize this object that I told you before, right? So always steep angle from the plane of S1. So here it doesn't look that steep, right? Probably I should draw that again, but these are going to be angles like this. Can you see that? If I were to put the plane here, remember this is like this, like that, and this is the axis that goes through the middle, so this is the axis that goes through the middle, then you will have these faults like this and like that. Same as before, the angle between the plane of S1 and the plane of S3, which in this case is now is SH mean, is going to be this angle from here to there, right? And that angle, same as always, is 45 plus friction angle divided by 2. This angle, right? From here to there or from here to there. So after you do that, how do you proceed? What I recommend is that in order to make this easier, you match the center of this cross with the center of your north, east, west, south cross. Because as soon as you do that, then you know that this angle is 20 degrees, right? And this angle here, in between that line that goes through the center and that line, and it's going to be the same as that one, is going to be 90 degrees minus this. And 90 degrees minus that, how much is that? That's going to be 31.7, right? So the strike is going to be this angle minus 31.7, this angle plus 31.7. And then just get the strike from there. So find this direction first. Find what that angle is. That one inside here is the same as that one. And then just add and subtract that angle. And you'll get the strike and dip. As we said before, the dip of this, either a hydraulic fracture or the shear fracture, is going to be 90 degrees. The strike of the hydraulic fracture in this case is going to be that line, this perpendicular to SH mean. So east 20 degrees to the south or west 20 degrees to the north. And this angle is going to come from adding to this angle over here. Either you subtract 31.7 or you add 31.7 and you get the strike. Okay, so are we good so far? No questions? No? Good. All right. So then let's move to 5. 5, you have to draw stereo nets. And for faults in different directions. Don't worry about this plot, okay? This is something I was doing before when I was asking students to solve for the projection of stresses on an arbitrary angle. So in this case, this is going to be the stereo net. This is a fault which is 55 degrees with azimuth and dipping 45 degrees to the southeast. So this is a fault that strike is this 55 degrees and it's dipping 45 degrees towards the southeast. So it's something like this, right? This plane is going to hit this lower hemisphere projection intersection in that line, and perpendicular to that, if we have a line that is perpendicular to that plane, that line is going to hit the lower hemisphere projection at that point. That is the point that you have to draw. Did you guys use that web application I sent you to draw stereo nets? No, well, let's take a look at that because it's much better than my drawings, and you can also take a look at that in 3 dimensions. So let's see. Wait a minute, this is stuck. So, are you guys reading my emails or not? Homework number 4. Okay. So, okay. Let's come back to this video later on, okay? So, you go here, and in this case, we said this is a plane that was, what was it? 55 degrees strike, 45 degrees southeast, right? So look, 55, let me get to 55, and now 45 degrees, somewhere over there. Okay, almost, okay? That is that plane. That's the same stereo net as, well, similar to the one we have there. You see that one? Oh, sorry. And all right, so what's going on? Come on. Okay, it's going to come up in a minute. How did you find this problem, guys? Was it difficult or okay? Just give me a sec that this one turns on. Come on, what's going on? Okay, I think now I should be good. Bless you. All right, it's going to show up in a minute. Let me check if the camera is still recording. All right, so there we go. We have the stereo net. That's a problem that you had to solve. This is the 2D version, and if you go to the 3D version, it's that plane. You see, this is the plane of the fault. This is the north over here. This is the strike, and this is the